So now let's switch gears and talk about defenses. Our next speaker is Kerem Arikhan from Binghamton University, and he's going to talk about how to build leakage-free caches.
All right. Thank you for the introduction. Hello, my name is Kerem Arikhan. I'm a third-year PhD student from Binghamton University, and today I'm going to be presenting TEE-SHirT, Scalable Leakage-Free Cache Hierarchies for TEs. This paper was a collaborative effort between co-authors from Binghamton University and University of California, Riverside. So I'm going to preface this talk by describing what a trusted execution environment is, which is abbreviated to TEE. So TEE is assumed that an application has to go through a potentially malicious system software, which can come in the form of an operating system or a hypervisor. This deems the hardware as the sole trusted computing base. So therefore, TEs allow applications to carve out a piece of themselves called an enclave. Enclaves are allowed to directly interact with the hardware for their memory management. So they don't have to rely on the system software for their memory management. Therefore, they can encapsulate and encrypt their data. This deems, so the threat model of this TEs are like basically system software is untrusted while the hardware is. So secure, right? Well, no. Turns out the information can still leak through enclaves through a plethora of research on cache side channels on Intel SGX, which is the most prominent example of a TEE. So therefore, the operating system can infer information from enclaves through cache side channel attacks. Well, why does this happen in the first place? Well, we assume that the system software can be part of an attack, right? Which has many capabilities, such as single-stepping to attack the higher level caches, such as L1 cache and L2 cache. However, the current literature mostly focuses on the last level cache as the primary attack vector. So the problem here is that current schemes do not cover this area. Cover this area mostly. So the problem here is how do we cover this area as well in our attack vector? Well, therefore, we introduce TEE-SHirT. So the primary question we answer is, how do we secure all cache levels without relying on the system software? Under this question, we make 4 main contributions. 1, scalability. 2, context switches. 3, cache coherence. And 3, security probability. Due to time constraints, we're going to focus on the first 2 bullet points, which is scalability and context switches. But for the other ones, feel free to refer to the paper, or you can have a conversation with me offline. All right. Before going on, I would like to go over how we implemented this. We implemented TEE-SHirT on Gem 5 cycle accurate CPU simulator. We also implement TEE-SHirT's key components on an FPGA prototype for hardware overhead estimation. We use Spec 17 and MeBench benchmark suits to drive our experiments, and we mechanize our operational semantics for the formal proof with COG framework. All right. Before going into details, I would like to introduce 2 main security paradigms when it comes to securing caches. So one is flushing and other is partitioning. Flushing is invalidation and writing back of dirty data to a lower-level structure across security domains. So we illustrate this on the left side of the slides. Here, we illustrate an enclave A context switch to enclave B. So currently, the cache is totally occupied by enclave A's data. So before context switching, enclave A has to invalidate and evict the dirty data to a lower level structure, which can be another cache or the main memory. So before the enclave B gets scheduled into this cache, it's completely empty, which disallows enclave B from interacting with enclave A's data residue. So through its natural workflow, enclave B populates the entire cache, and therefore this is secure. The second approach is partitioning, which is the actual spatial division of the security domains into dedicated cache boundaries, which are called partitions. So this requires the provisioning of each tables to each security domain, in this case enclaves. So the remapping hardware, when the cache is accessed, diverts the cache access within its corresponding partition. And therefore, upon a context switch, we do not have to evict or invalidate anything. Just enclave B accesses the table, and the table diverts the access. So there's no spatial collision between these 2 security domains. All right. So to summarize, flushing is the temporal division of security domains, whereas partitioning is the spatial division of security domains. With this out of the way, the question we ask is, how do we secure private caches individually? because these two caches exhibit very different characteristics. For example, L1 caches are frequently accessed and low latency, and typically smaller than L2 caches, 2 to 64 kilobytes. On the other hand, L2s are high latency and less frequent, and typically 256 to 512 kilobytes. So the question is, how do we apply these aforementioned paradigms to these private caches, starting with L1? When we implemented flushing on L1 cache, it exhibited very negligible performance degradation, proving that flushing across context switches and system calls seems to be a sufficient solution for L1 caches. So the reason why this happens is across context switches, the data of an enclave is naturally evicted from the cache anyway without implementing flushing itself. So there is no performance gain to be made from data retention in the first place. Same does not go for L2 caches, though, which exhibits up to 60% performance degradation depending on the operating system time quantum. Well, why does this happen, though? There are two main reasons, both of which are stemming from the inclusivity property. The reason why we consider inclusive caches in our paper is, one, they're especially vulnerable to side channel attacks, and two, they greatly decrease the amount of hardware needed to implement cache coherence mechanisms. Well, what is inclusivity property? This property ensures that the line in a lower-level structure, let's say the L3 cache, should also be present in a higher level, let's say L2 cache. So as you can see here, the cache lines A, B, C, D should also be present in L2, and since L2 is also inclusive, these lines should be in L1 as well. Well, there's a problem with this when LLC is partitioned. The problem is, if you, let's say, have a 32 kilobyte partition in L3, you effectively limit the size of your private caches as well. So you basically have, even if you have like a 1 megabyte L2 cache, your effective size is basically 32 kilobytes. So inclusive partition caches effectively limit the capacity of private caches as well. The second problem is when flushing is implemented in L2 caches, this flushes also trigger a back-end validation for the maintenance of this inclusivity property. So the overhead from these back-end validations is also an additional source of performance degradation. Okay. When we get to LLC, we don't make any claims here. Prior literature already establishes that LLC has to be partitioned anyway. So if you want to see these claims substantiated, you can refer to these papers that we cite here. All right, with these out of the way, basically our security composition for TEE-SHirT cache hierarchy is as follows. L1 data and instruction caches are flushed across context switches and system calls, whereas L2 and L3 caches are partitioned. We also ensure how cache coherence is established between these caches, but the details are in the paper. You can refer to the paper for that. Okay, so this gets to our first contribution, which is scalability. How do we support high number of enclaves with minimal hardware? So why is this a problem in the first place? Well, as we mentioned, partitioning requires additional metadata associated with each partition. So as the enclaves proliferate, the amount of table that you have to provision for each enclaves also increases. So let's assume like you have 1,000 enclaves, and you have to provision like 1,000 tables for each enclave, which is infeasible. So we illustrate this in the next slide, where we show how not to manage partition metadata. In this example, we have n+1 concurrent enclaves running in the system. So the mapping hardware provisions n+1 tables corresponding to each enclave. Cache also has n+1 partitions with more room to spare. But let's assume that an enclave n+1 gets scheduled into the CPU. Now, the problem here is that the mapping hardware does not have enough tables to accommodate this enclave in the CPU. So what happens is that this enclave has to replace another one, which in turn results in a deletion of its metadata, which in turn results in a flush of its corresponding partition. So therefore, the maximum number of concurrent enclaves is limited by the number of tables provided by their mapping logic in this configuration. We remedy this through leveraging a baseline Intel SGX functionality called processor reserved memory, PRM for short. PRM is usually used for data encapsulation, encryption, and thread metadata management. We extend the data structures within PRM to also include the metadata that is correlated to each enclave. So let's say in a similar manner, we have n+1 concurrent enclaves running in the system and n+1 metadata correlated to each enclave. In this example, though, there are two currently running enclaves, not concurrently, currently running enclaves, and there are two tables now correlated to each currently running enclave. So let's assume enclave n gets scheduled into the CPU. It replaces enclave 5. Now the enclave n is correlated to this table, which has the context of enclave 5. So what TEE-SHirT does is it loads the context correlated to this enclave automatically, which replaces context 5. So in a similar manner, if enclave n+1 gets scheduled into the CPU, we basically have to allocate a partition and create a new metadata associated to this partition, and upload that metadata into the processor reserved memory, and we are good to go. Therefore, we alleviate the context switch and system call time penalty and ensure lower hardware complexity, since we do not have to provision as many tables as concurrent enclaves. All right. So we evaluate this through looking at slowdown inflicted by cache flushes when metadata virtualization is not implemented. So the bar graph here shows the slowdown when it's not implemented, and the yellow lines here show the number of system calls on the right side of this y-axis. So what happens here is that if you don't implement metadata virtualization, you have to flush. Let's assume like you have to flush every single partition each when a context switch happens. It goes above 10% for some benchmarks, depending on how many system calls there are. So the takeaway from the slide is basically that system call intensive programs tend to benefit the most from partition metadata virtualization. Our next topic is context switches. How do we implement context switches? And why is it a problem in the first place? To see how context switches cause correctness issues, let's consider this case where an enclave X, which has its own area and partition in private caches, gets scheduled across cores. So as you can see, the partition and the area that is correlated to this enclave lingers on the old core. So how do we handle this? TEE-SHirT handles, so we already established that when enclave gets descheduled from the cache, L2 caches are flushed. So when enclave X gets scheduled in the core 1, this scheduling gets notified to the L1 cache, which in turn flushes the previous contents. So now this scheduling has to be relayed to the L2 cache, which in turn does two things. One, it allocates a new partition, which in turn creates the correlated metadata and flushes the old contents across cores. So this results in a metadata update of this enclave, which has to be relayed to the last level cache. So currently, since the last level cache is shared across every single core in the system, the partition here can stay idle. So the metadata here is not updated. However, the change still has to be relayed to the memory management unit for later use. So for example, if this enclave gets descheduled and has to be rescheduled into the same core, this metadata has to be correct. Therefore, we update these PRM pages. So TEE-SHirT ensures that new partitions are allocated inside private caches on cross-core context switches. Next, we look at the overall evaluation of the system, where we evaluate TEE-SHirT on a 4-core system with 5 benchmark mixes, so 20 benchmarks in total. So the takeaway from this slide is basically that if we eliminate the overhead that is caused by the minimal partition sizing, the total overhead of TEE-SHirT goes below 5% across all benchmark mixes. So with appropriate sizes, even memory-intensive benchmark mixes yield reasonable performance results. Please refer to the paper if you want to learn more about formal security analysis of TEE-SHirT, cache coherence support, and integration of TEE-SHirT with Intel SGX. With this, I conclude my talk, and I'm ready for your questions.
Let's thank our speaker. If you have questions, please line up. I have a question. Mm-hmm. So the design that you described sounded very general to me.
Yes.
And the sort of for your implementation, you have implemented it on SGX. Mm-hmm. But have you looked at other TEEs and whether they're as easily extensible to be able to support TEE-SHirT?
So depending on which enclave which TE you're focusing on, trusted computing base varies a lot. So the most so the smallest, we looked at the smallest TCB, so which is TEE-SHirT. So sorry, which is Intel SGX. So Intel SGX only assumes that the hardware is supported, right? Hardware is trusted. So the question we ask, okay, how do we ensure that only using the hardware, how do we secure these caches with just the hardware? So this would work on other TEs as well, because other TEs, include other components of the development stack also. So this is the most.
So when the TCB is larger, so they're doing more sort of in software, right? But they should already have.
Yeah, the smaller TCB. So since it's a smaller TCB, this will apply to other designs. Basically, this is what I'm trying to say.
Any other question, comment?
Hi, I'm Fan from Georgia Tech. So I have a quick question about, could you provide a little bit detail about how you go from the Gen 5 simulation to the support for Intel SGX? Because one is a simulation, you said it is ready for Intel SGX, right? So
yeah, we make in terms of like evaluation, we have to make assumptions here. So we reserve a portion of the DRAM to contain these metadata that is related to these like partitions. So yeah, we basically emulate the behavior. So whenever we need to do a context switch, we do a mock access to these areas and load it to the structure that we implement in the caches. So that's how we account for the access delay.
I see. Okay. Thank you.
You're welcome.
Other question? Let's thank our speaker one more time.